In the previous example, we had a melting snowball where the volume was a function of radius and the radius was a function of time. So we could write a new function for the volume as a function of time by taking the composition of those two functions, where we put the function for the radius in terms of time into the volume equation and create a new function. So we just have to give it time and it would give us volume. Now we saw that in order to get the rate of change of volume over time, we could multiply the rate of change of the volume with respect to radius times the rate of change of the radius with respect to time. And so now we're going to generalize that, and this is going to become the chain rule, okay? So if you have two functions, y equals f of z and z equals g of x, right? For some inside function g and the outside function is f. And we're going to assume they're both differentiable. And if we have a small change in x, it generates a small change in z, and the small change in z generates a small change in y. And like we saw before, we can multiply these rates together. So the change in y over the change in x is equal to the product of the change in y over the change in z times the change in z over the change in x. Okay, so we're just multiplying the rates together. And in the limit, as that delta x gets smaller and smaller, the dy dx or the delta y over delta x becomes dy dx, and the dy dz or the delta y over delta z becomes dy dz, and the delta z over delta x becomes dz dx. Okay, so here we have the chain rule. All it's saying is that if we have the composition of two functions, we have y as f of z and z is g of x, and we want to find the rate of change of y with respect to x, then we can multiply the two rates. The rate of change of y with respect to z times the rate of change of z with respect to x. Now we can write this in another way using function notation. So essentially what we're doing is we're taking the derivative of the outside function and leaving the inside function as it is, right? And then multiplying times the derivative of the outside function. All right, this is going to make more sense once you see it in action. So let's take a look at example 3. And so in each of these, we're going to have an outside function and an inside function. Now, you'll get to the point where you can just write down the derivative directly. But for the purposes of this video, I'm just going to, since you're just learning it, I'm going to break it down. All right, I'm going to say y is going to be, I'm going to call that my outside function. And I can see a sign on the outside with a 2x minus 1 inside of it. Okay, so I'm going to make y equals sine of z. And I'm going to make z the inside function, 2x minus 1. Okay, so I'm just pulling those two functions apart so I can see the inside and the outside function. Then I'm just going to take the derivative of each one. dy dz is equal to cosine of z. And dz dx is just equal to 2, right? Just equal to 2. All right. Now if I want dy dx, all right? This is dy dx now. It's not dy dz. We had dy dz up here. Now we want the derivative with respect to x. Okay? So I'm just going to multiply dy dz times dz dx. Okay, that was supposed to be 2. I'm going to multiply cosine of z. Now, I want to write everything in terms of x, so I'm going to replace z with 2x minus 1, and then I'm going to multiply all of that times 2. Now, it probably makes sense to put it in front. Usually you would put it in front so that it doesn't look like it's part of the, that's inside the cosine somehow. So I would probably write it as 2 cosine of 2x minus 1. And that's it. That's it. We're just multiplying dy dz times dz dx. All right, the derivative of the outside function, but you leave the inside alone, right? When you write that derivative, right? It's just z, and then we take the times the derivative of the dz dx. Derivative of z, dz dx. Okay. Anyway, let's go on. Let's go on. All right. So I'm gonna break this down. I'm gonna call q, since I have the variable q. I'm gonna call that e to the z, okay? Because I'm seeing e to some power, but the power is a more complicated function, so I'm going to call that the inside function, and that's going to be minus 0.25 t squared, okay? Take the derivative of each one. dq dz is just e to the z, and dz dt is equal to, okay, bring down the 2 and multiply by the constant that's already there. So I'm going to get 0.5, and then I subtract 1 from the power. So negative 0.5 t. All right, so now we're just going to multiply those together to get dq dt, right? Now we're finding the derivative of q with respect to t. All right, so we're going to take dq dz, that's e to the z, but I'm going to replace z with what z is, which is negative 0.25 t squared. So you see how in the derivative of the outside function, you just leave the inside function as it is, and then you multiply that times the derivative of the inside function. Okay, so those two things are multiplied together. Now it might be a little bit better form to put the negative 0.5 t in front, and then e to the minus 0.25 t squared. Okay, that looks a little better. So especially when you're multiplying by the negative, you don't want to look like subtraction. So that's why I put the parentheses around it. All right, we got a couple more here. All right, but you get the hang of it. Feel free to pause the video at any time if you want to go ahead and try this on your own. All right, so again, I'm going to pull this apart into the composition of two functions. V, I'm going to say, okay, I have 7 times something to the 5th power. So I'm just going to make that 7z to the 5th. And inside the 5th power, right, I have this z, which is 3t squared plus 4t. 3t squared. 3t squared. All right. Now we're just going to take the derivative of each one of those things. dv dz is just going to be 35z, oh my, 35z to the 4th. Oh goodness. All right, let's try this again. 35z to the 4th power. Z to the, this is a 35. All right, there we go. 35z to the 4th power. Stay. And then dz dt is equal to 6t plus 4. Okay, let's take the derivative of each one, and now we're just going to put them together, and we're going to end up with dv dt. Okay, so 35, and then we have z to the 4th, but z, we have to replace that with what z is, which is 3t squared plus 4t. And then we're just going to multiply. Multiply by 6t plus 4. 6t plus 4. All right. Oops, I forgot the 4th power and all of that. All right. So notice how I replaced z with what z is, so that we have everything written in terms of t, right? We need to write it in terms of t. All right. I think I got that. All right. One more. All right, so again, I'm going to break this apart. I see a constant times a square root function, and inside the square root, I see 3r minus 2. So I'm going to make a equal to pi square root of z, or maybe, well, maybe I'll just do z to the 1/2 power. Z to the 1/2 power. Okay, and then my z is just, goodness, z is equal to 3r minus 2. All right. All right. All right, so now we're just going to find dA dz. All right, so I get, now, depending on how I remember, I just usually like the power rule. So I'm just going to write it, actually, I'm going to write it pi over 2, right, to bring the 1/2 down, and then z to the minus 1/2, or you could write it as 1 over the square root of z. That's fine too. Okay, stay. Oh my. Okay. And then dz dr is equal to 3. Okay. Nothing disappeared. So now I'm going to write dA dr, right? The derivative of a with respect to r is just going to be the product of these two. So I'm going to have pi over 2, and then times z to the negative 1/2 power. So 3r minus 2 to the minus 1/2 power, and then all of that times 3, right? Now I could write that as, it looks like I have 3 times pi in the numerator, so I can make it 3 pi over 3 pi over, what do we have? 2 times the square root of 3r minus 2. I could write it that way if I wanted to. Either one is fine. All right, so there we go. We have had to get some practice with the chain rule. I'll meet you in the next video.